This video is specifically for Dataflow Geometry learners who appreciate mathematical proofs. So in it, we're going to cover, first in 2 dimensions, an important theorem called the enclosed angle cosine theorem. And then we're going to build off from that to prove the point axis projection theorem. And then we'll move into 3D and see how we can extend and prove both of those 2D theorems and, in fact, a whole class of plane geometry theorems in 3D. It's something called the glass pane meta theorem. Well, let's get started first by exploring the relationship between trigonometry and direction vector math. Both are centered around the unit circle. We've got a point here, and it's going to scope out all the points on the unit circle. And if we were to just pick one of those points and look at our trigonometry relationship, we've got an angle theta, which is taken from the positive x-axis over to the ray going out to that point. And from our basic trigonometry definitions, since we're working in a unit circle where all the hypotenuses are equal to 1, then our sine theta is going to equate to the y-coordinate of the point, and the cosine of theta is going to equate to the x-coordinate. Okay, so on the direction vector theory side, we don't need angles to get those points or those x and y coordinates. What we can start with is just a point in space here, point P, and if we just normalize that vector, we can establish this point on the unit circle. So let's take a quick look at some of those. And now you can see here we're going to observe the normalization of this point vector is a graphically editable point. If you look over here at your numbers for it, you'll see that what we're doing is carving out that same unit circle, going around it, but this time we're visiting numerically thousands, maybe a million different points on that unit circle. All this done all computationally through a very simple calculation. What we're doing to get this direction vector, the yellow direction vector, is to normalize the point vector P. And so we're just essentially scaling it by 1 over its length. Now, we still get x and y components of this point. And yes, these still correspond to the cosine and sine of the angle, which in this case, it would either be a very large positive angle coming all the way around almost a full circle from the positive x-axis, or it could be a negative small angle. So given these 2 different approaches to the unit circle, we can start to unify them with the following identities. So we can identify this point of direction vector as having x and y coordinates equal to cosine and sine of the corresponding angle theta. And then if we wanted to go backwards from direction vectors into angular space, there is a method in modern numerical real number libraries on computers called ATAN2. It's an arctangent, but you have to feed it both the y and x components of the direction vector in order to put this theta in the correct quadrant. If you don't have both of these, there's going to be an ambiguity, which is really one of the, from a modern perspective, is one of the detriments of traditional trigonometry. We have inverse functions like arctan that aren't really functions because they're ambiguous as to the result. So we're going to move on now to develop out a couple of the most important theorems that we're applying in Dataflow Geometry 2D. And these are both closely related to our use of direction vectors. The first is called the enclosed angle theorem. And this is the one, we've seen this hopefully already, where we're in the unit circle and we've got two direction vectors, d1 and d2, and an angle theta, which is the enclosed angle, or the angle bracketed by d1 and d2. And the theorem simply says that the dot product of d1 and d2 gives us the cosine of that angle. And this is very useful. It also works the same way in 3D, which makes it ever more useful to know this and to apply it. In terms of proving it, probably the simplest way I could describe it is to just say this is a special case of the dot product of two vectors. So if you've seen this, the dot product of vectors v1 and v2 is equal to the length of v1 times the length of v2 times the cosine of the enclosed angle theta. Well, we're in the unit circle, so our vectors both have lengths equal to 1. So that's one way you can arrive at this theorem, although it does beg the question of how do you prove this. And I'll have to admit, I had to look hard to find a proof, and one was never given when this was introduced to me in all my years of schooling. I have finally seen one. It's fairly complicated and hard to follow. So I'm going to give you another simpler proof using trigonometry from the 11th century. Okay, so how am I going to do this? Well, what we're going to do is treat this angle theta as the difference angle between theta 1, which bridges from the x-axis out to d1, and then theta 2, which bridges the x-axis to d2. And as you can see, so theta is the difference of the angles theta 1 minus theta 2. And so what we'll do is our first step is to take the cosine of both sides. That works. If the two angles on both sides of this equation are equal, then the cosines also have to be equal. And this is where we get into the trig, and this is credited to Al Hazen, one of the stellar mathematicians of the Islamic Golden Age in Baghdad and Cairo, and he published this around 1021. But he was the first to solve for this trigonometric problem. How do you get the cosine of the difference angle, theta 1 minus theta 2? Hopefully we've all seen his result. And so it's fairly simple now to get to what we want, because if you can just recognize here that what's being done is we're multiplying the x components of, if we write out the vectors this way, right, this is the dot product of two vectors, right? So you multiply the x's to get the result here, you multiply the y's to get this, and then you add them together for the dot product. Well, just going backwards, then the thing we're starting with to arrive at this must be these two vectors and their dot product. And then we can just simply recognize the first of these is D1, so it's cosine and it's sine. D2, cosine of that angle and sine of that angle. And voila, we have a much simpler proof than if you try to go through and unravel everything that's going on with this statement here. So this is very useful. We call this the enclosed angle theorem as pertains to a pair of direction vectors. The other important theorem, and this probably even surpasses that one in importance to what we're doing in Dataflow geometry, is the point axis projection theorem. Now, I know we hauled this out and used it without proving it first, but I did intend to eventually get to this point where we would look at the assertions and prove them. And so just to restate, what the theorem says is we have a point P, and we have an axis which is represented by direction vector as an alternate x-axis. So dx is the direction vector. And if we want to obtain the coordinate that P would have when projected onto this axis direction, call that x prime, then the theorem states for any point P and axis direction dx, the coordinate x prime where P projects onto dx is this simple calculation. So the point dot product direction vector for the axis, P dot D. Okay. Well, it's very useful, and it's very simple, and it's a very robust calculation. It never fails. So it's eminently useful computationally. But let's see if we can prove it. It shouldn't be that hard, especially now that we have the enclosed angle theorem. Okay, so let's try doing the following. So we've got a right triangle here. Let's just ink in the hypotenuse. And what we'll do is actually also ink in this direction pointing to the point P. And we'll also consider drawing in this angle theta, which bridges between the two directions. Okay. Well, just from the simplest trigonometric definition of the cosine, it's the adjacent over the hypotenuse, correct? Well, we can rewrite that as this length of this leg of the right triangle, x prime, is equal to the hypotenuse times the cosine of the angle theta. So this is just basic trig for cosine. And what we're going to do next is to use the enclosed angle theorem and substitute for cosine theta. Well, what does that theorem say? It says that the cosine of this angle theta can be obtained as the dot product of dx and dp. So we'll substitute for cosine theta just that dot product. Okay, so we're pretty near to being done with this. Basically, what we're going to do is just take this scalar value, the length of P, and move it inside the parentheses. We'll multiply it times this direction vector, D sub P, before doing the dot product with D sub X. And we know we can do that. It's just a scalar number. As long as we just multiply it times one of the vectors, we'll not change anything. And so look what we've got here. We've got the length of vector P times the direction of the point vector P. And so we're literally just going to reinflate that into the point vector P. So this is replaced by P. And we're really just doing something backwards that we can always do with a vector or a point vector, and that is to factor it into its length and its direction. What we're doing is the opposite here. We've got its length and its direction, and we now want to combine those through scalar multiplication, and that will reinflate the original point vector P. So this is our result. It wasn't that difficult to arrive at. If you wish to look at the case where the point projects over onto the negative axis, I encourage you to take that on. If you have any questions about this working, you will find that you do come out with an x prime that has a negative value, and you'll see how you arrive at that. But it's a fairly simple extension of what we've done here to just look at the other case where the point P is projecting either from above or below onto the negative extension of this axis d sub x. So with that, I'll just summarize by saying that the direction vector math we're using in the course, yes, it may strike you as new and unfamiliar. And once again, the reason we're introducing it early on in the 2D geometry treatment is because of its profound value when we make the leap to 3D geometry. So essentially, we won't have to relearn very much new going from 2D to 3D. And that's the primary advantage. The other one, which I've stated in the past, is that for sake of computability, the direction vectors are much easier to merge into algorithms than are angles, because the direction vectors are extremely well behaved and they don't posit any singularities or degeneracies once they're constructed. And we'll see that this point axis projection theorem in 2D works exactly the same way in 3D. So changing to that 3D topic, let's just start by visualizing what 3D direction vectors look like. So here we are in 3D. We've got our axes. So we've got x going out to the right. We've got y going away from us and z going up. And the gray sphere represents the unit sphere, the sphere of radius 1. And so what we'll be doing in 3D is representing pointing directions in 3D space using direction vectors. And if you look over on the left, you see the yellow one in the middle of the column, and you can see how its pointing direction is just represented by the coordinates x, y, and z of a point on the unit sphere. Same with the green and the red. All right, so let's take a quick look at our cosine of an enclosed angle. Well, let's just focus on two of those directions, and we'll see how this dot product in 3D is going to work. So if you look over on the left side, we've got two direction vectors. I can mouse edit those. I'm calculating their dot product. You can see it here numerically. And then assuming that produces the cosine of the enclosed angle in 3D, where if we take the arc cosine, that should give us the angle in radians. Well, as you can see, we're starting out with the two directions almost equivalent. I see the yellow one is just almost the same. Now, if we start spreading these apart, you'll notice that our cosine value, which is the top number, is coming down and our angle is increasing. And if we keep going now, we've passed the point where these are perpendicular, that when they're exactly perpendicular, the dot product should go to 0. It's just about right there. And if we keep spreading them further, we should be able to get them almost to -1. There we go, just about right there. And so our angle should start to approach pi, or a half circle. The other proof we can visualize first here graphically. So we want to take this orange point and get the projection coordinate on this magenta axis. And so all we're doing here is calculating a 3D dot product. And you can see the value will go negative if we're out here on the negative portion of the axis, goes positive out here. If we change the axis, it all works exactly the same. So we're negative, we're positive. And the calculation just looks like this, where we're going to multiply the x's from v1 and v2, multiply the y's, multiply the z's, and sum those up. And that gives us our 3D dot product. Okay, so let's turn our attention now to seeing if we can prove these things. We just saw a convincing demo that the enclosed angle of two direction vectors does produce the cosine when you take their dot product. And we just saw that the dot product works to project a point onto a 3D axis. The big question here is, can we prove these? So we're going to develop some logic I call the glass pane meta theorem for computational 3D geometry. So it begins with this question. So just think about any provable plane geometry theorem. This is going to apply to all of them. When working in 3D geometry, does the same theorem hold if the objects described by the theorem are all contained in one 3D plane? Well, intuitively, yes. So for example, here's the Pythagorean theorem, well proven in 2D. What if we're working in 3D and we've got a right triangle? None of its edges are aligned with an axis, but the two edges labeled A and B are mutually orthogonal. Does this require a separate proof? Or here's another one. So Euclid gives us this beautiful proof in 2D, the intersecting chords theorem. Two chords within a circle, A times B equals C times D. What if we're working now in 3D with a tilted 3D circle? Does this require any additional proof? And so what we're working towards here intuitively is a meta theorem. So it's a theorem about all 2D plane theorems, plane geometry. And so the thinking goes like this. So here's a plane that we would use for developing a 2D geometry theorem and proof. It's got x and y axes. And when we move up to 3D, we're just adding this third axis z. So we can think of this plane, which is spanned by the x and y axes, as equivalent to this thing mathematically. However, when we're working with computation, there's a distinction between these, because in 2D, all our quantities will be 2D points, directions, and when we move up to 3D, now we're going to be handling three-dimensional points and directions. But we know that since the xy plane in 3D may be rotated computationally or just conceptually to any other 3D plane, So maybe this magenta plane, or it could be rotated out to this red plane. And since 3D rotation preserves all the spatial relationships within the plane, then if we can prove that a 3D theorem's content is all coplanar, then the 2D theorem's proof suffices to prove the 3D case. Oh, okay. And we call this the glass-pane meta-theorem, and the visualization of the theorem just comes out of the fact that we can imagine a 2D proof being etched or sketched on a pane of glass, and then in 3D that pane is picked up and rotated, and so all of the assertions must still hold. Okay, so how can we use this meta-theorem? Said we wanted to be able to prove the 3D case for the enclosed angle cosine theorem. So now our direction vectors will be 3D, D1 and D2, and we want to prove that their 3D dot product will still give us cosine of theta. So how can we prove this? Well, now that we have that meta-theorem, we can just sketch in 3D. There's our two 3D direction vectors, D1 and D2. There's the enclosed angle theta. And we just simply ask if all the 3D content of this theorem lies in one plane. And we can see there are only 3 points involved. So there's the origin, there's the tip of D1 and the tip of D2. And the vectors connecting them lie in that same plane. We know it generates a plane or determines a plane because that's an axiom of 3D geometry. And so the glass-pane meta-theorem applies since all the content is in that one plane. And this is all we need since we had already proven the 2D theorem. So this is now done for 3D. And so we have the second theorem in 3D, which is a 3D point projected onto a 3D axis. And will it be able to give us the coordinate of the point on that axis? So here's our sketch. We've got point P. We've got an alternate axis here specified by positive direction D. It's a 3D direction vector. And this is what we're trying to get, is the coordinate that P would have, just a single scalar number. And this is our assertion that this will work. And so that now the proof can fall out in a very simple way. So is the 3D content all contained in one plane? Well, again, it's 3 points and only 3 points involved: the origin, the tip of D, and point P. 3 points spawn a plane that allows us to apply the glass-pane meta-theorem. The 2D theorem was adequately proven. Boom, we're done with this one. And one question might come up in regards to the difference between 2D and 3D computation, and that's, wait, what about the dot product? It's defined differently in 2D versus 3D. Are we talking about the same thing mathematically? So this is our definition of the 2D dot product, vector dot product. So multiply the x's, multiply the y's, and then add the result. And this is it in 3D. So we've got this additional multiplication where the z coordinates get multiplied and then added. Well, we can show that these are essentially the same thing by using the glass-pane meta-theorem's corollary, and that just states that for any 3D plane PL, there exists a coordinate rotation operation that will rotate plane PL to PL prime, where PL prime is essentially folded back onto the one of the axis planes. We might as well just arbitrarily say it folds back onto the XY plane. And this effectively collapses the 3D plane PL down back to a 2D plane. And the glass pane is simply realigned parallel to a pair of 3D axes, or the XY axes, so that all the coordinate variation is squeezed back into 2D. And we know we can do this computationally. Okay, so let's just take a quick look at the computational approach to doing that. So we have plane PL at some arbitrary orientation. We can assume it started as a plane in the XY plane and got a rotation applied to it. That would imply that the origin is contained within the original plane and the rotated plane. So we're going to now see what it takes to put that plane PL back onto the XY plane. We know that we can orchestrate a coordinate rotate, and if we define the new z-axis of that rotate using plane's orientation, then after the coordinate rotate, the plane prime's orientation has to point straight up the z prime axis. Why? Because we said that we would define the new z prime axis using the plane's orientation. Now, since 3D rotations are reversible, this means we can transform a plane from XY, standard XY axes plane, out into 3D, and then using this transform back to exactly where we started in 2D, because the rotations are reversible. Okay, so now if we accept that the 3D dot product calculation is correct axiomatically, we can easily show that the 2D dot product is merely a special case of it. So we'll start with the 3D dot product as axiomatic. If we form the mutual perpendicular direction of A and B as their normalized cross product, and then assign it as the z prime axis for a coordinate rotate, here's what we're doing. We're doing the normalized cross product of A and B, and when we rotate these vectors, what happens is that all of the information is rotated into the x and y coordinates, and the z coordinate will be 0. So the effect on their dot product when we multiply these two vectors is we get 0 for the third term of the dot product, and that essentially shows the equivalence of these two formulations of the dot product, so long as we have this ability to form this coordinate rotate operation. So our conclusions are simply moving from 2D geometry to 3D, our intuition that we can reuse every 2D theorem in 3D, so long as the 3D content lies in a plane, is correct. And it helps to visualize the 2D proof sketched on a pane of glass and then picked up and tilted any which way, scaling it up into 3D. And the glass pane meta theorem formalizes this intuition by rotating out an axis-aligned 2D plane with geometry content into an arbitrary 3D plane, and then just reversing that rotation. So bottom line, we can be fully confident that geometry computations, not just the math theory, but the computations, will work when extending our plane geometry know-how for 3D.